D3 dynamics. And Newton's 3 laws. Now, the first law of Newton we can consider to be a law that Galileo discovered. And basically it's that if a body is, say, in a state of rest, it wants to stay in a state of rest. If it's moving, it wants to stay in a moving state. Now, think of this as being in outer space where there's no friction and things like that, because frictional forces will slow things down. Like if I do that, it stopped because of the frictional force. But if I did that where there's no other forces to get it moving, when it starts moving, it's going to keep moving. We can consider this Newton's first law, and I like to think of that as the law of inertia. That if a mass is, say, at rest, it wants to stay at rest, and if it's moving, it wants to keep moving. In other words, it wants to persist in the state that it's in, and you need to apply a force to change that, which brings us to the second law. If there's a net force, and I say net force because forces can cancel, like if I pull one way here and the other way, then the pen will stay where it is because the forces are canceling out. There's no net force on there. If I pull too hard, I actually pop the lid off, the cap off. Okay, so here, if there's a net force, then there is a change in the motion. So think of the law of inertia, no change in motion, because the total force is 0. The net force is 0. So you can think of this here, the net force is equal to 0. And since force has magnitude and direction, we can write it with a little vector sign on top. Then if there's a net force, then there's a change of motion, there's an acceleration. And the famous equation is the force is equal to the mass times acceleration, F equals ma. So if you have a large mass and apply a force, then you get a certain acceleration. But if that mass were to be smaller and you had the same force, then the acceleration would be greater to keep the equation the same. And then the third law is action and reaction. That every force has an equal and opposite reaction. All right, so if you have, say, a force, you apply a force on a block like this, and say this is your hand or your finger pushing that block, then that block is pushing back on you with an equal force. So these are Newton's laws. The law of inertia and F equals ma. So inertia, the key idea there, F equals ma. And the law of action, reaction. Now, since Newton's law involves forces and forces are vectors, we can write F equals ma in vector notation, where you have a magnitude of force and also a direction. And the acceleration is the rate of change of the velocity. So we can write this as a derivative like that. So we can write Newton's second law as m dv dt. Now there's an interesting question, because in physics we have a definition of momentum as m times v. Now the question is, should that derivative really be moved on the outside? Should the law, now I'm asking this as a question at this point, should it be d mv on the inside, say, dt? And the answer to that question is yes. And that's easily seen if we think of a rocket problem. So if we have a rocket that's shooting mass out the back, then the mass of the rocket is decreasing. And that mass that's decreasing going out the back gives a kick or a force for the rocket to go. So you need to consider that in general. Let's go ahead and do that in one dimension. F would then be equal to d mv dt, which would be equal to, using the product rule, dm dt times v plus the mass and the derivative of the second one, using the product rule. Derivative of the first times the second plus the first times the derivative of the second. Now, if we're losing mass, let's consider that case where we're losing mass. Then dm dt is less than 0. So what I'm going to do is I'm going to say that the m dt is, by definition, I'm going to set that equal to 3 equal signs, minus alpha, where alpha is some parameter that's greater than 0. So that means dm dt is going to be negative. All right. So if we do that, I can then bring this alpha v to the other side of the equation and have f plus alpha v equals m times the change of the velocity with respect to time, which is the acceleration. So we have this extra piece. So now, if you were to be pulling on the rocket and the mass is shooting out the back, there's a one-dimensional problem going out the back, then this would give you more of a kick to get more acceleration. Now, if you're going up, say your rocket's going up and this force of gravity is pulling you back, then by shooting the mass out the back, you would have to have this term be greater than the one going down so that you would have the rocket go up. So this is an interesting way to think about the mass changing, and the more general formula being the change in the momentum with respect to time. So in other words, the force is equal to dp, where p is mv dt. However, in your introductory physics classes, you pretty much 99% of your problems are that the mass is constant. You don't even think about rockets. In fact, there may not even be any rocket problems in the first introductory class. But I just wanted to make this subtle point, since we are introducing Newton's laws, and technically this one should be replaced by this one for 2 reasons. Because first, you want the vector form to have the general form, and also the momentum is the correct formulation of the second law. But among friends, we often say F equals ma.